Thanks. It's nice to be here. Nice to be here in Miami. It's good to see a Python community down here. I've actually spent a lot of my life in South Florida. Not a lot of people know that, but between like family and so forth. So I probably spent like a couple of years, over the last 25 or 30 years down here. So. Nice to be back in the sun. It got down. I just moved to Nashville, Tennessee, and it doesn't get cold there, and it got cold just as I was leaving. So perfect. So so last year, for a variety of reasons, I founded a nonprofit open source development group. And this is not the kind of thing that you hear about happening very often. Usually when people want to work on an open source project, it's something that they're working on as their hobby, like they work on it on nights and weekends, and they push code to GitHub. Unfortunately, recently we've seen some major security breaches in the Node package manager, and in some of those cases it was like, hey, I was just having fun building this software, and somebody came along and wanted to maintain this module, and I said, sure. And they didn't bother, verifying their identity, and there were certain protocols that were not followed. But I think a lot of people do open source because it's fun, and if it weren't fun, well, probably a lot less of us would do it. People do open source for many other reasons. Often it's because they're solving a problem that they have at work, and they, for whatever reason, they want to give the work that they're doing either send the contributions upstream into another open source project, or they feel like they've built something that's interesting and it's filling a gap that exists in the world, and so they decide to open source it. Pandas, which I understand that many people use, started out as a closed source library, and I made the pitch. This was like early 2009. It's like, hey, it would be really great if we had a nice library that a lot of people used, that a lot of people used that made data easy to work with. You can read data files, you can manipulate it, you can do analytics. It'll be great. So I think at that time there was sort of skepticism, like, oh well, are people even going to want to do this work in Python at all? And that now at least people nobody asks that question anymore. But there's other people build up open source projects in other ways. Sometimes they start companies, and so lately you've probably seen a lot of articles. Everyone's sort of wringing their hands because it's very difficult for open source projects to have successful business models when Amazon Web Services or another software company that doesn't do a lot of open source can take the software, build a software as a service offering, and then not give any code back to the project. And so we've seen many high-profile open source projects like Redis, Apache Kafka, well, not Kafka itself, but Confluent, the company one of the companies started by the founders of Kafka. So companies have been changing their licenses essentially to try to make it harder for AWS and friends to take from the open source world and not give back. And so it's getting harder and harder to build open source software sustainably. And so, as I've been working on the Arrow project for a little over 3 years, and I decided I didn't like any of the models for funding the work that I saw, particularly given how much the project is an infrastructure project. It's not a product. It's not like a service that you set up and run. It's not a database. It's not something that could be turned into an Amazon service offering. Maybe some part of it could, but I wanted to really, have a group of engineers who are focused on, building high-quality software that the world can depend on, and help the ecosystem, the data science ecosystem, but also many other programming communities evolve their computational foundations into the future. So I've been doing that, and that's kept me pretty busy, over the last year or so. I mean, thankfully, we have a number of gracious sponsors who are funding the work, and we're growing a team. So things are going well. So as part of this, I wanted to partner with the R community, and so the first time people on the internet found out that Hadley Wickham and I are friends, it sort of produced all of this, like, what? Like, R and Python people can be friends with each other? Like, isn't that, it's like not allowed, right? It's like, it's cats and dogs, like, Montagues and Capulets, that kind of thing. And it's like when I get together with people from the R community, yeah, we're writing different code in different programming languages, but these days, a lot of us are writing C and C++ code. A lot of us are solving the exact same problems, but we're delivering solutions to different communities. The R community happens to be more skewed towards the academic statistics world, and certain, and so in data journalism and communities where the Python hasn't historically had as much penetration. Python has more machine learning and kind of computer science in different communities. So it's great for us to be working together. We are now 5 full-time engineers, so I'm very happy to be putting 5 people to work full-time just doing open source software and nothing else. We're also working with some folks from the RStudio Tidyverse team, people you may see out in the wild contributing to Apache Arrow or other projects. And my shameless plug is that we are still hiring, and so if you or anyone would like a remote software engineering position in a large open source project, please let me know. So we have a number of sponsors. So from the get-go, I partnered with RStudio to make the business of growing a team of employees and engineers easier for me, so that I can spend more time focused on building software, less time on running a business. And I have run a business in the past. Like I founded a startup called DataPad 6 years ago. So I've had the experience of doing all of the accounting and business stuff, and so I wanted to do less of that and more software. Before this, I spent 2 years working with 2 Sigma, who have been great sponsors of the Arrow project. NVIDIA, who are out in force here at this conference, are sponsoring the work. We just received sponsorship from the Open Data Science Conference, and you might think it's weird. I've got to put this on Twitter. I haven't done it yet. I'm just in the process of updating the website, but you might think it's interesting for a conference to sponsor an open source software development group, but I mean, you think about the relationship that conferences have with open source software. Conferences are growing and have revenue because the open source software is popular, so it's not that strange. And I hope that we see more conference organizers giving money back to open source. So there's other ways that sponsors can help. So NVIDIA just donated these 2 big workstations, which are now keeping my apartment really toasty. So I just don't even need to turn the heat on anymore. And they're not that toasty because cryptocurrency mining is not really profitable right now. So we are only running CUDA for Arrow development, and I'm probably not supposed to joke about that. It is a joke after all. But it's great to have other kinds of support, because software development requires tools. We need tools like these to be able to make sure that we are building software that can run on this kind of high-end equipment, which gets used in many different environments. So anyway, with all of that out of the way, I'm going to get to the technical stuff. So I'm going to make some broad generalizations, and so please don't nitpick the details too much, although nitpicking the details is important. But after I started working on the Pandas project in 2008, and after 5 or 6 years, we had built the project. Myself and the other Pandas developers had built the project based on the technology that was available essentially in 2007, 2008. So that was NumPy, SciPy, Matplotlib, IPython, CPython itself. And if you think about NumPy and these scientific computing libraries, they in turn are providing a Python API to do array computing, matrix operations, linear algebra, using techniques and software that was available in the mid-90s and even before that. So there's like a lot of Fortran code for linear algebra that was available in the 80s and 90s and even the 1970s. And so there's kind of this huge legacy of computational software that is powering modern data science. And some of it has scaled well to current hardware, and some of it has not. Some of it also the problems have to do with just the software development. So Pandas was built so that every operation, every line of code, every function call is immediately evaluated. And so that works well when your data is a megabyte, but it doesn't work that well when your data is a terabyte. So just things like the way that code is evaluated has to change when you want to think about working with larger data sets. When you're working with a lot larger data sets, the way that you manage memory and the way that you access data has to change in order to be more scalable. Another problem that I experienced, and this is partly in interacting with the R community and other open source communities, is the fact that even though we're solving many of the same problems, we're kind of working independently. Like we don't collaborate very much. We don't share code very often. If we all have data frames and we say the word data frame, but if you go under the hood, our data frames look different. And so, I couldn't help but think like, well, what if we could try to address some of these problems and also make it easier for the different communities to collaborate? And so in an ideal world, there's not really any rocket science. It turns out that there's a rich literature of computational techniques for large-scale data processing. The analytic database world has been solving large-scale data processing problems since the 80s and 90s. There's a rich literature that can be mined for techniques for working with a lot larger data sets and tools like Pandas. So ideally, we would build everything to be multi-core native. Now we have GPUs. So even though Moore's law is sort of over for CPUs, like the scalability curve is like still going and going and going for GPUs. So we have to take advantage of that if we want to keep scaling into the future. We have all these fancy runtime compiler tools. So gone are the days of having to hand generate x86. Like we can use LLVM to generate code, efficient code at runtime. We can think about how we can share, now that systems have become a lot more heterogeneous, we can think about sharing data more efficiently between systems. So there's a lot of stuff we can do. And one point that I often make is that the reason why we haven't had to address these problems so much in the past is precisely because of Moore's law. And we've been able to say, well, things aren't great, but we'll just wait a couple of years and things will just magically become faster because processors get faster because Moore's law. Also, the RAM will get bigger, so more data fits in memory, so we can kind of just punt on thinking about these problems. So the Arrow project was conceived in 2015, kind of serendipitously as a group of 20, 25 open source developers that I had connected with, mostly out on the West Coast, who were key people in various big data projects. And I had just started working at Cloudera, and I wanted to somehow mind meld the data science world with folks in the big data and the database community. Because traditionally, like I started telling them about pandas and about data science, and I'm dealing with a bunch of people with PhDs in database systems, and they have never, they don't know anything about R or Python. They've never really experienced this world, and so there's just this kind of like has historically been no collaboration happening. And so what I would like to see is to enable these communities to collaborate and for the data science world to be able to benefit from all of the research and ideas that have been generated in the analytic database community in the last 30 years. So when we started the project, the single problem that we wanted to solve was to define an open standard for representing tabular data in memory. And so Pandas has its own way of representing data. R has its own way of representing data. Every SQL database engine has its own internal runtime format. So we can't be all things to all people, but it would be nice to have some kind of a reasonable open standard that could be used to power analytical applications. So thankfully, 3 years have passed, or almost 4 years have passed since we started even talking about the project. And so it turns out that a lot of people agree that it is a problem. And so what we would like to see, and I understand that Clément from NVIDIA also spoke about this, but we kind of want to get away from this world where we're having to do all of this conversion between point A and point B all of the time, and at least have some kind of a way of representing data at the memory level, so in RAM or in shared memory, like memory maps, where assuming that two systems know about Arrow, that they have the option of sharing data with each other using Arrow. Is this thing working? I'll use the keyboard. So now that time has passed, we started out with Java and C++. We're now up to 11 programming languages. So we most recently added C# and MATLAB to the mix. So I think other languages that we don't have that would be really interesting, I'd like to see Swift. People are talking about Swift, so any Swift programmers, like this could be a project to work on. We have Rust. A lot of people are programming in Rust. But in terms of the work that we're doing in the project, and this is my opinionated view, so we're focused in a few key areas. So the first is that we want systems to be able to share data and share code. So if you want to share code, you need the data representation to be the same. Otherwise, you say, well, this table looks a little bit different from what my code expects, so I have to convert it to my expectation and then run my code. So if the data is an immutable standard, then if you have two algorithms which know how to interact with Arrow memory, then they don't have to be rewritten. Because Arrow is a brand new data representation, we have to implement connectors into storage systems and file formats. And so we've been spending a lot of time doing that. We want to enable systems to share data with each other through different protocols. So whether that's through shared memory and memory maps, or through on a network. So if a system says, hey, rather than going through ODBC or JDBC or some other kind of database protocol, say here's my port which exposes Arrow data natively, and so we can move data around a network without having to convert to some intermediate representation. So as you can imagine, this is very ambitious, and it's been a difficult project to work on. And we're working kind of with two kind of high-level goals. So the first is that we want the platform of libraries and all these programming languages to be a suitable development platform, like a foundation for new systems to be built. So if you are building a new database, you're building a new data frame library, maybe you're building like a data microservice, like you want to have a service that can receive a table, apply like a small operation to it, and then send the data onward to some other service. We want to make those things easy to build. And we also want to be able to retrofit existing systems with kind of algorithms and tools that are coming out of this out of this ecosystem. So that would be like, like the Pandas ecosystem, for example. We'd like existing data frame, like data science projects, to be able to benefit from this. All right, I use the keyboard. So it's kind of like the mnemonic for thinking about system architecture. I didn't intend to become a computer scientist. I was a mathematician. It just anyway. So traditionally you build a system and you build this kind of vertically integrated thing where you got to make your own data structures. You've got to build data connectors. You write your own algorithms. Maybe you design your own file formats. If you need to move data around in a distributed system, you define a wire format for moving data around. So we'd like to develop standards to kind of address all of these problems at the same time. So we have standard data structures. We don't have to serialize. We have reusable algorithms, reusable file formats, and we can move data in a distributed system in a standard way. So if you ever look at the architecture of a database system, usually in a database, you just interact through the front end. The front end is often SQL queries. And the other parts of the system you don't really see. So there's an in-memory, like a way that data is managed in memory. There's the query engine that does select, join, group by, where, and so forth. And then there's back-end storage. And there's I think one of the things that the Hadoop ecosystem did over the last 10 years was decouple the storage, like the file persistent storage, from the database system. So this idea of like bring your own database and like all the data is in the Hadoop file system. And now cloud storage like S3 and Google Cloud Storage has taken the role of this as well. So what we would like to do is kind of decouple all of these components and give them a public API. So if you need to store and serialize data, we can do that. If we need to compute queries, traditionally databases would not expose the details of their query engines to library users. But the thing is, the front end, that's kind of opinionated. Like maybe some people like SQL, some people like code that looks like pandas. I don't want to dictate what the user API looks like, so that if somebody wants to build something that's eagerly evaluated, they can do that. Something that's lazy, something that's SQL. But we can have many different ways of interacting with these components that don't require an opinionated interface, or even an opinionated programming language. So you wouldn't be required to use Python or use R. And in fact, like it's been really exciting that we're working with folks in the Ruby community in Japan who, we write something in C++, and within a few weeks we have ways to interact with that code in R, Ruby, and Python. So it's kind of a brave new world. Like I've never worked on a project like that before. So this is kind of rehashing the things that I was just saying. I said them out loud. So I kind of want to rewind, or like at least take one step back a little bit into the practical domain of the Pandas user. You say, okay, Wes, like this all sounds great. We're going to make new systems really fast. We're going to make systems more interoperable. We're going to have all these libraries and all these programming languages. Sounds great. How is that relevant to me? Because every day I go into work and I write import pandas as PD, pd.readcsv, and then I'm off to the races. So I gave a presentation a little over 5 years ago, and the title of the presentation was 10 Things I Hate About Pandas. And a lot of people thought that was funny, but it was really kind of constructive criticism about the internal implementation problems of kind of how Pandas is implemented, like how it's designed, and like why those are causing issues. And it was not to say that some of these things are fixable, and so this was before we had categorical in Pandas, and so that's resolved some of the problems with strings. But in general, like if you have really big data that doesn't fit into memory, and ideally you could memory map that. Very difficult to do with Pandas. So people have been tackling the out-of-core, very large data problem with other tools like Dask, and Dask has been a great tool for helping scale pandas. The way that pandas represent strings is really inefficient. So they use a ton of memory, and there's basically no way for computational code to process them efficiently because they're all in the Python object heap. And so if you've never really thought about this, and this is from my collaborator Uwe Korn's slide deck. So if you have a pandas series, like a data frame column that has strings, it's representing those strings in a NumPy array that contains Python objects. And so each Python object has a pointer into various objects all over the, wherever Python allocates strings. So not only is the memory that represents the string all over the process heap, but the struct, like the C struct for the Python string is large. Like it actually, from Python 2 to Python 3, it got bigger. So if you're using strings in Python 3, I know we're all really happy to only be using Python 3 now, but right? It's 2020, it's almost here. Yeah, it's this is more serious than Y2K, really. I mean, yeah. So even if you have a string, even an empty string, like an empty string in Python 3 takes up 48 bytes. There's just it's length 0, 48 bytes. There's no way around it. So, so one thing that Uwe, who's one of the Arrow developers, has been able to do is use extension arrays in pandas to extend. I already set this up for myself. To extend pandas with Arrow string vectors, which have kind of like a packed, kind of contiguous memory representation. They use a fraction the amount of memory that Python strings do. At least the overhead is 4 bytes instead of 48 per string. And all the data is contiguous. So just by having a more efficient representation, use a lot less memory, you can process the strings a lot faster. So, so there's some other things like allowing data to be non-contiguous, like having data frames composed in multiple chunks. We don't really have tools for dealing with nested types, so I don't know if you've ever run into that problem where you're processing JSON and you need to kind of unravel the whole data structure before you can do anything. So my view is we should have operators to just process the data in place and do so efficiently. So these are problems that we're tackling in Arrow land. So I've been talking a lot, so I don't want to run out of time, but I'm going to tell you about a few things that we've been doing that are cool, where the benefits of this work are playing out. So one thing we did with my colleagues from 2 Sigma, and also worked with folks, Brian Cutler from IBM, so other folks and folks in the Spark community have been involved at all, is that we made custom Python functions on Spark run a lot faster. So now if you're using Spark, I think 2.3 and higher, there's now a special pandas UDF where you can write extensions to Spark SQL that use pandas operations and can have up to 100 times better performance. And so it's a bit crazy that the performance is so much better when you consider how much work is actually happening. So when Spark SQL is evaluating these pandas UDFs, it's actually performing 4 separate conversions to and from the Arrow memory layout. So Spark SQL has its own table layout because every system has its own table. This is kind of pre-Arrow systems. So it converts to Arrow, which gets streamed over to the Python worker process. That gets converted to pandas, and we've gone crazy making the conversion from Arrow as fast as possible. The pandas operation is evaluated, and then the data gets streamed back to Spark via the Arrow format. And even with all of those conversions, we're still able to get 100x speed up in some cases. So You could imagine like how much, well, I mean, I guess we'll find out, but you could imagine how much better the performance would be if both systems on the left and right were both using the same memory representation and didn't have to do all of this conversion. I presume since you've been at this conference, you've heard from folks on the Rapids team. I see now I'm not supposed to say NVIDIA Rapids because it's a community and there's other developers, but the Rapids libraries started by NVIDIA, but they're built around the Arrow memory format for representing data frames on the GPU. So super exciting stuff to see so much kind of GPU analytics code getting built. So it's been exciting to work with all of these companies and different open source collaborators around the world. So I want to tell you kind of briefly about things that I'm focused on and things that we want to build, because there might be some things that you run into in your work. And the biggest way that a lot of the Python users and developers can help is that we want to hear from you about the problems that you're facing. If something is slow, if it doesn't work well, if there's something you can't do, something seems too hard. Like that's feedback that's really helpful so that we can help, we can prioritize and take into account the use cases and the experiences of people out in the community, because ultimately like we're building software that we want to be widely adopted. I'm not building software for a product or anything. I have no ulterior motives. Like I just want to see the ecosystem develop and become more efficient. So we're spending a lot of time on file formats. That's things like I'll mention the file formats. We have started building a high performance messaging framework called Flight. I'll say a few words about that. We are collaborating with folks building an LLVM array expression compiler that's specialized for the Arrow memory layout. We are going to be starting to build an in-memory query engine that's similar to an analytic database engine that can be run in process and embedded in many different places. And obviously, we want to make sure everything works really well for kind of the major data science communities in Python and R. So this is, if you're really interested in how the open source project works, but we release software, we build stuff. I'll let you look at this. So one thing that's been interesting I want to mention about things that we're doing is that one way we've been growing the project is by recruiting people working on problems that are one step away from Arrow, but where essentially the work that people are doing is almost the same. Maybe they're already using Arrow, or they could be using Arrow with a little bit of effort, and saying like, why don't we join forces and work together to solve common problems and build libraries that we can ship as part of the same ecosystem. And so we've been so that's part of how we've grown to so many programming languages is by identifying groups of open source developers who started building something that is kind of already effectively in the Arrow ecosystem, but they're working independently and say, hey, we've got this community here. It's an Apache project, open governance, it's independent. Let's work together and kind of have a cohesive community. So that's been it's been a lot of work for me. It's been a lot of paperwork, but it's been very rewarding. So on the file format side, I assume that a lot of you are familiar with these file formats. The requirements are being driven in large part, and I'm going to stop and take questions soon, but the requirements are being driven in part by these are the formats that are used in modern data warehousing in the cloud and in the Hadoop world. So we need to be able to read and write all of those as efficiently as possible. Project where I just started working on in late last year that I'm really excited about is standardizing data transport in a distributed system. So like the rest of the world, we're buying in on gRPC, which is Google's messaging network library. Really great piece of software. So what we were doing is, you connect a client to a server, and you request a data set, and that data set gets streamed via gRPC in a sequence of Arrow messages that are using the Arrow protocol. And we did some low-level work in gRPC so that we can receive the message and begin to compute on it without having to do any deserialization. So there is like network cost, but basically we want to saturate the network and not have any serialization happening on either side. So compared with some other protocols, like some cool things we can do is parallel retrievals. So instead of having one data node, you have many data nodes, and so a client could be fetching a large data set from many different servers on a network, and that can provide scalability in a scenario where you want to distribute large data sets to many different clients and where the data is maybe sharded across many different servers. Another very exciting project is Gandiva, which is named after the legendary bow of Arjun in Hindu mythology, if I have that right. So it's a very fancy bow that can shoot arrows very fast. And so Dremio, who's one of our one of the major collaborators on the project, started this project. It's written in C++. It uses LLVM, and its focus is on evaluating the computations that are part of the select part of a SQL query and the where block. And so these are often bottlenecks and where where SQL systems will try to squeeze out CPU cycles to compute those as efficiently as possible. So Dremio is written in Java. There's a limit to how fast you can go in Java, so hence LLVM. So it's really exciting that from a Java system, so because we have Java libraries and C++ libraries that are representing data in RAM in the exact same way, so a Java-based database engine can send a data set along with a description of the computation it wants to perform as like just a general, it has a serialized representation of expressions. So they're sent over as a protocol buffer. That expression is compiled with LLVM. And the cool thing is that even though the data was allocated in Java, we can act on it in process in C++ without any copying. So even though there's JNI, it's just sending pointers. And so it says, hey, C++ runtime, compile this thing, here's my pointers, run this thing, allocate some memory, send it back. So traditionally, sharing data between the JVM and Python and the C++ world would be impossible. But it turns out it's not impossible, it's just a lot of work because you have to define this, data protocol and like memory format and like there's like 7 layers of technology that we've had to build to make all this possible. Yeah, boring stuff. We need to work with the cloud, so it is what it is. But anyway, I'm going to stop here and take a few questions. But so this has been a really exciting project for me, in particular. Now that we've gotten out of the early stage where it was I had the experience of doing makedir a bunch of times and starting a brand new code base. And so now we have a fast-growing community in all these programming languages and people all over the world. So a very exciting time, and I think the next few years are going to be really cool. And I'm glad to have sort of the Ursa Labs nonprofit arrangement so that so I can prioritize the needs of the open source world and also work with corporations who want to sponsor the project. So if you have the ability to sponsor or know anyone who can sponsor, please let me know. Otherwise, I will see you on GitHub. Thanks.
Thank you, Wes. Any questions?
Hi, thank you for coming to Miami. A question that I have is any known company having Arrow already in production?
Yeah. So Dremio. So they're the first production users of Arrow from like very early days. And so I mean, Dremio is a product, but it's a distributed database system, and it's being used in, I don't have their customer list, but it's being used in production in many places. The Arrow libraries are being used in production by Python people at a pretty high rate, as far as I can tell. We're at somewhere around like 1 million installs month over month, which is quite a lot. So I think the two big use cases there are reading and writing Parquet files and storing and memory mapping large data sets or moving them around. Also kind of using, Arrow is being used in production with Spark. So I think if you're a Databricks customer, you can use Arrow in production on Databricks. If you're using Spark 2.3 or higher, you can install all of this and run production Spark jobs that use Arrow. But I think this customer kind of contributor list is, I need to update it, but we have folks from Alibaba, Ant Financial that are using, Uber is a user. Like, I don't know, you've probably heard of some of these companies, I guess. Yeah, I would say the diversity of use is increasing, and that's a good thing as far as growing the developer community.
There's a lot of software written to use NumPy. Do you have any sort of vision for how to either port or replicate that?
Well, I guess NumPy is designed for a different use case. So, for example, multi-dimensional arrays. We don't do multi-dimensional arrays. So this is about tables and analytics. So data is primarily one-dimensional. It comes through as like a stream of chunks, and so kind of it's intended to work in tandem with NumPy and TensorFlow and things that are working with multi-dimensional arrays. So it's a complementary thing, not a replacement. If that makes sense.
First off, I'm super stoked about Arrow. Like, the spec looks really awesome, and I'm really excited to use it in a Pandas data frame. One question that I had about future directions, if there were any, I've read most of the spec, and I was really excited to see nullable data in like a bit array mask. And I think that was one of your points in your 10 things I hate about Pandas talk, is like how weird null data is in Pandas.
Yeah, I didn't mention that here, but it's. I think I should add that to the slide. Null data is weird in Pandas, and so addressing the, where's that slide? Somewhere up here. Yeah, so I'll add it to the slide, but yeah, addressing the kind of weird rough edges and inconsistencies with null data was also a big motivation. So in Arrow, there's a bit for each value. The bit is on if it's non-null and off if it's null. One of the cool things about that is that if you have a batch of data that has no nulls, you can just skip checking for nulls. And if you can use hardware operations to count really quickly. So I wrote like a blog post about this recently. That basically we should stop using sentinel values and use bits instead. Anyway.
But by extension, I guess my question was taking nullity to the furthest degree where you have like really sparse data. This came up in Richter's talk yesterday. I've tried to use like the Pandas sparse data frame before and found it to be kind of not, it looked like kind of unloved, like it wasn't being developed really actively. And I was wondering if there were plans to incorporate sparse data into Arrow and then via that Pandas later.
Yeah, I think that the sparse objects in Pandas are even planned for deprecations and removal. So sorry to hear that, but I think the way that we would address sparse data in Arrow is with run length encoding. And so it's been discussed, but so far there isn't a proposal around like how to incorporate it into the specification. And so I think there's one thing to say you run length encode data in memory. A lot of database systems already do this. But I think the real question is if you want to be able to send run length encoded data from one system to another. And so that's where we would have to do some like evolve the specification to accommodate that. There's also kind of the desire to compress data on the wire. And so far we've been concerned with like random access memory mappable representation and not dealing with compression, but that's also, like there's a JIRA open about it, but that's something that we eventually have to have in the protocol.
So I have like two small questions. The first one is, do you see any sort of like pandas rewrite, or ideally in the future it's going to be a rewrite of any of these libraries, or it's always going to stay kind of in the fence, in this outer layer as a front end? And the second one is if you can like really quickly tell us about the Apache incubation, how that happened, how Arrow got into Apache, and what are the benefits, just completely out of curiosity.
Okay. So the first question around rewriting pandas, that seems unlikely. So there's a couple of things. So pandas is an extremely large library, and the way it's designed, it is not very amenable to extremely large data sets in the way that the library works. And so we've spent a lot of time, like the Pandas core developers and I, like we all met up last summer in Austin, and this is one of the topics that we discussed. So I think that the consensus is that we want pandas to continue to be like a hugely featured, like super big Swiss Army knife of working with data, with a very wide, large collection of APIs, very flexible for working with, low gigabytes of data and on down in memory. Obviously, Dask Data Frame and other projects will continue to use pandas like as a black box for doing out-of-core algorithms, and so that's been going really well. But I think my interest is in building a essentially companion project might be one way of putting it, but a library that's designed for working with very large data sets and data sets that are largely on disk, where you need to select, filter, aggregate, join, essentially more like a database, but embedded and in process rather than being a database system that you have to run. And that will all be Arrow powered and something that could be used together with pandas. In parallel, of course, I think there's some parts of pandas where like we have code that we're maintaining, like that could be retrofitted with stuff that's coming from the Arrow libraries, and that will mean less code to maintain for pandas and better performance as well in some cases. So it's kind of a bit of both, but I think like a grand kind of API compatible rewrite of pandas is not in the cards. The second thing is, so we decided to do a project in the Apache Software Foundation, mainly to head off concerns about kind of governance and like competition amongst vendors. So like a number of the individuals who helped start the project worked for big data companies that are in direct market competition with each other. And one of the ways that the ASF helps is by providing like a neutral ground for competing vendors, like the people that work there, to still collaborate and say like, oh, we can't have one company with a ton of money come in and take over the project. Like the ASF like helps protect the other developers from corporations with lots of money. So we formed we split some IP out of the Apache Drill project to create a new top-level project in 2016. And so we were kind of a top-level project from the get-go, which spared us some of the trials of the incubation process that a lot of projects often have to go through.
All right, final question here.
Do you have any remarks on the new data class feature in, is it 3.6 or 3.7, and its usefulness in the Pandas Pandas workflows, Arrow, or other interesting applications of that new feature?
I haven't looked carefully enough to have strong opinions about it. I will say that I think it's good that the language moratorium has been lifted and that new features are being added to Python. I mean, I think if data classes can be used to make like nicer ORM-like features, like I think there were already, maybe some people in the room are familiar with traits. Like anyone ever used traits before, or traitlets? So this was like a long time ago. There was essentially something very similar to data classes, where it would do type validation of attributes, and if you set a value that was the wrong type, it would error, things like that. And maybe I think data classes seems maybe like a more, I maybe have the feature set wrong, but it seems like it's a good thing. So, and if it can be made to work well, kind of together with Pandas or other tools like this, then that's great. So,
Thanks again, Wes.
yeah, thank you.
So we've got another session of talks starting in here, and then a tutorial starting at 2:15. Might run a couple minutes late to give you guys more of a break.